Hello everybody, hope you guys are doing well. So today we will be starting with operating systems. This is by Galvin. He's a very famous author. Okay, this is the 10th edition, and now why do you need to study operating systems, right? I mean, what's the aim? Like, why do you need this? So like when we are thinking of servers, right? For example, maybe uh, when we have a proxy in proxy like nginx or something like that. Now these are basically built on top of operating systems, right? So you need some processing as well whenever an request comes in there. So at that time as well, you would be like using various concepts like for example, uh, nginx has like it does not do um but it has it does like a forking, right? So that, and like what is a fork call, that we will like see once we go in detail. But then again, so what I'm trying to say is, like even if you are at like if you're working like a proxy on nginx, maybe one over will be Apache Tomcat server, which is a very old proxy, which is not like many companies are shifted to nginx. So like there's some kind of work that needs to be done whenever a request comes in, and then certain concepts like multi-threading will be used. So our goal is basically to understand what these concepts are. So basically these are operating system related concepts. Nginx will kind of acts on top of OS. So we will study like what are these, what is this. Okay, this is the preface, and then okay, then what does this book contain? First is like what topics are we going to cover, even like memory management. It is all based on operating system, right? So the first thing that we will study is like what is an operating system. I mean, why do we need an operating system in the first place? Like how they are designed, how they are constructed. So, and then we will be studying about different types of what do you mean by kernel, what happens then. And then we will be studying about process management, basically something like concurrency. So like we want our operating system always to be occupied, right? So like what is the difference between concurrently processing something, like how to achieve that. Then and so there are different processes, right? So like there are different applications running on your operating system. Now how to determine, so basically we can't determine which operating system, which application will get the CPU time, but then we can um, like manage them. So we study about stage transition diagrams, then how inter-process communication occurs, that is communication between processes. Then we need to synchronize the processes, right? For example, if there is a data transfer, or there is certain things need to be done. Now the one of the most important features is memory management. How is the memory managed? How is IO operations done? Then another thing is security and protection. So protection again. Then we will study about something like, so the NFC or the TCP is on the operating system, right? Again, we will look about that. Then this is basically Linux based little bit uh, OS concepts. Then we will study about the virtual machine, and then we will like what is multi-core systems, what is virtualization, what are non-volatile memories. Okay, so chapter 1 basically will include like what are multi-core systems, what do you mean when you have So right now we have more than one, right? Like we have multi levels of CPU. So what are those? And then why do we need a multi-core? What is multi-threading? um then we will study something about NUMA systems, Hadoop clusters. Okay, now operating system also provide like what is Android operating system, what is the iOS. Then we'll study simplify further processes, thread and concurrency, especially this is the most important. We have multi-threading, concurrent programming. What is that? Then synchronization, CPU scheduling, like is how the scheduler in the CPU works, what are the different algorithms used for scheduling. And then synchronization again is basically inter-process communication, how to synchronize them. Deadlock is basically a critical condition that occurs. Then how to detect deadlocks, what can we do to avoid deadlocks. And then this is memory. First is the HDD or the hard drive, that is the RAM, not the main memory. Then we will study about virtual memories, for example. uh, other We have also have a secondary memory, right? HDD, how do they work? Then what happens during an IO operation? Then how what is RAID, what is cloud storage? IO is basically when you have like a keyboard connected, right? So when you press some buttons, an IO operation happens. So then how does that happen? What is the advantage? Like what all steps needs to be done before. And then we have file more about file structures. Like then in virtual machines we'll deal about what are Kubernetes containers, Dockers, what are those. This is basically again it will be on Docker network and distributed. Remember operating system also is the NFCs on the operating, right? So again that will be. Then we will study about little bit about a Linux system, like the Linux kernel, the Windows operating system or the 10, and then the appendix. Okay, so today we will be starting with our first chapter, like what is an operating system, why do we like why it is so important. So this is basically what is an operating system, what is computer system organization, what is an architecture, what is kernel, like what is security, what is like an overview about operating system. Then we will be studying about system structures, process management again, inter-process communication or IPC mechanism, what happens. Then we'll study about threads and concurrency, what do you mean by multi-core and multi-threaded programs. Again this is very important. Now what are the scheduling criteria, what are different types of algorithm that we can do. Then process synchronization, this is basically when we need to do two process communication, right? They need to be synchronized. Then we will study about deadlocks. Deadlock is basically how to avoid a deadlock in a situation. Main memory, virtual memory. Then again what is the copy on thread optimization, a very important thing. Then storage management, HDD versus RAID structure. What is HDD? Then IO related thing. Then now the core part about Linux is how it's file systems, right? So then we will study a little bit about that. Then how cryptography can be used for protect, little bit about protection. Then again this is basically how RTC IP stack is built on. Okay, so now we will start with the first chapter. So then we will see what do you mean by an operating system. An operating system is software that manages a computer's hardware. It also provides a basis for application programs and acts as an intermediary between the computer user and the computer hardware. An amazing aspect of operating system is how they vary in accomplishing this task in a wide variety of environments. Operating systems are everywhere from cars, homes, operating appliances that include IoT, smartphones, computers, enterprise computers, cloud computing, everywhere. So what he's trying to say is operating system is something, it kinds of acts as an interface between user and the hardware. because they use in olden, like even in the DOS OS, this was the drawback, right? So like if you are able to so hardware is where all the information is stored, right? So think of a cloud as so a cloud is basically, there are actual physical data centers, right? Even if you do cloud computing, you say it's on the internet, but then there are physical hard drives, right? Data will be stored on them. So what if there is no one in between the user and those drives? Your data is lost, right? That will be a major security concern. Also, you will be able to perform a variety of things which we never intended to. So then the operating system was defined to act as a interface uh, between the user and then the hardware. Now, because an operating system is large and complex, in order to explore the role of operating system in modern computing, it is important first to understand the organization and architecture of a computer. This includes CPU, memory, and I/O devices. A fundamental responsibility of an operating system is to allocate resources to these programs. Because an operating system is large and complex, it must be created piece by piece. Each of these pieces should be well delineated portions of the system, which carefully define input, output, and functions. In this chapter, we provide a general overview of the major components of a contemporary computer system as well as functions provided by the OS. Additionally, we cover several topics to help the stage for remainder of the text. Data structures using operating system, computing environments, and open source and other free operating systems. Okay, now what operating systems do? As in beginning in the discussions, we define that a computer system like we begin a discussion by looking at the operating system's role in our overall computer system. A computer system, computer system can be divided into three different parts, right? One is the hardware, then is the applications. Now these application programs are run by the user. Hardware is basically the IO devices, right? So hardware, we have the CPU, and then other physical ports like the USB drive, the hard drive, the other parts. Now the hardware is basically where the CPU, the memory, and the IO devices are connected. The application is basically, for example, Microsoft Word, spreadsheet, web browsers. These are all programs, right? These are basically used to solve computing problems. The operating system will control the hardware and coordinate its use among the various applications for various users. We can also view a computer system consisting of hardware, software, and data. The operating system provides the means for proper use of these resources in operation of the computer system. An operating system is similar to a government. Like a government, it performs no useful function by itself. It provides an environment within which other programs can do. So what basically the operating system does is it provides like a guideline in such a way that the CPU is always utilized. So the main goal is to utilize the CPU as much as possible. User view. The user view of the computer varies according to the interface being used. Many computer users sit with a laptop or in front of a PC consisting of a monitor, keyboard, and mouse. The system is designed for only one user to monopolize its resources. The goal is to maximize the work that the user is performing. In this case, the operating system is designed mostly for ease of use, with some attention paid to performance, security, and none paid to utilization. So users view. So the user's view of the computer will vary according to the interface being used. Many computers users sit with a laptop or a PC. Such a system is designed for users to monopolize its resources. The goal is to maximize the work. So then this is how the operating system is. So I have the user. The user will press the application programs, for example, compilers, browsers, software development kits, etc. And now the operating system is in between. So the role is to basically, it will, for example, when we write a print program, right, we want to enter it from the hardware. So then this permission will be given by the operating system, or the operating system will convey it to our hardware. Now many users interact with mobile devices such as smartphone, tablets, devices that are replacing desktop and laptop computers. These devices are typically connected to networks through cellular or wireless. The user interface for mobile computer is generally a touchscreen, whereas the user interacts with system by pressing and swiping fingers across the screen rather than the physical keyboard on the mouse. So what he's saying is, so there can be different types of users depending upon the requirements. For example, a person could have a computer, another person could have only a laptop. There is no external devices connected. Then some other person could have a phone, right? Some computers have little on use. For example, embedded computers. Then again, we have these are specific use cases devices. For example, embedded computers may have numeric keypads and turn indicator lights on off to show status, but their operating systems and applications are designed primarily to run without user intervention. Embedded computers also have an operating system, but then their goal is something to run without the user intervention. The system view. From a computer's point of view, the operating system is the program most intimately involved with the hardware. In this question, we can view as the as operating system the resource allocator. A computer system has many resources that may be required to solve a problem. For example, it might require certain amount of CPU time. It might require some data from storage, then some input from the IO devices. The operating system will act as a manager of these facing new resources. Facing numerous and possibly conflicting requests for resources, the operating system will decide how to allocate them. Yeah, so what happens is you might have two games running, so everything will require a GPU, right? So like nowadays we have a GPU, right? A graphical processing unit that specifically does the graphics thing. But then, for example, if you're running two programs like Word and spreadsheet, you can do multitasking, right? So then it's the role of the operating system to decide the CPU time should be given to which. Defining operating system. Now you can probably see the term operating system covers many roles and functions. That is the case, at least in part, because of the myriad designs and use of computers. Computers are present with toasters, cars, ships. They are the basis for game machines, cable tuners, and industrial control systems. To explain this diversity, we can turn to the history of computers. Although computers are relatively short, they have rapidly evolved. Computing started as an experiment to determine what could be done and quickly moved to fixed purpose computers. So for initially there was fixed purpose computers that could do fixed functions such as code breaking and trajectory plotting for government, and then for census calculation. Now those are basically those early computers involved into general purpose multifunctioning mainframes. That's when operating systems were born. In 1960s, Moore's law predicted that the number. Okay, then yeah. So then in 1960s we started using semiconductor, right? So then we said the number of transistors on an integrated IC circuit will be double every 18 months, and the prediction as held through computers gained functionality shrank in size. So initially there were fixed purpose, then we moved to general purpose, and that is when operating systems came into use. Now in general we have there is no exact definition of operating systems. Operating system exists because they offer a reasonable way to solve the problem of creating a usable computing system. The fundamental goal or the major goal of computer systems is to execute programs and to make solving user problems easier. Now, computer hardware is constructed towards this goal. Since bare hardware cannot solve this, applications are developed. Now, these applications require certain amount of certain operations for controlling the IO devices, the functions of allocating memory, controlling, and then these are all then brought together by the the operating system. So now every program will have a different goal, right? Some might require something, some might require some processing. So the operating system kind of decides like who should get what. In addition, there is no universally accepted definition, but in simple mind we basically say that it includes everything a vendor ships you when you order the operating system. The features include however, very gently across some systems become less than a megabyte of space, lack than a full screen editor, whereas other requires gigabytes of space and are based on graphical windowing systems. A more commercial definition, the one that we usually follow, is basically that the operating system is one program running at all the times of the computer, usually called the kernel. Along with the kernel, there are two types of programs: the system programs, which are associated with we will come to know more about it. What is the kernel? What is the system programs? The matter of what constitutes an operating system became increasingly important as personal computers become more. So it started becoming more and more software as things started developing. In 1998, the USA Department filed against Microsoft, and essence claiming that Microsoft included too much functionality in its operating system and thus prevented application vendors from competing. For example, a web browser was an integral part of Microsoft. As a result, Microsoft found guilty of using its operating system vulnerability to limit competition. However, if we look today at the operating system for mobile devices, we see that once again the number of features constituting the operating system is increasing. Mobile operating systems not only include a kernel but also middleware, a set of software framework that provides additional services to application developers. For example, each of the two most promising mobile operating systems are Apple's iOS, Google's Android. So why study operating? Although there are many practitioners of computer science, only a small percentage will be involved in the creation and modification of an operating system. Then why is there a need to study an operating system? Simply because almost all code runs on top of an OS. Knowledge help us to knowledge of OS will help us is crucial to proper, efficient, effective, and secure programming. Understanding the fundamentals of OS, how they drive computer hardware, and what provide to applications is not only essential to those who program them but also highly useful to those who write on programs them and use them. Okay, now the computer system organization. Now, in modern general purpose computers consist of one or more CPUs, and these are connected through a common bus that provides access between memory and shared memory. Now, each device controller is in charge of a specific device. A disk drive, an audio, depending upon the controller, more than one device may be attached. For instance, one USB port can connect to a USB hub, which several devices can connect. A device controller maintains some local buffer storage at the special purpose registers. Device controller is responsible for moving data. Typically, operating system have a device driver for each device controller. Okay, so now the modern computer consists of one or more CPUs and a number of device controllers that are connected to common bus that provides access between components and shared memory. Each device controller is in charge of a specific type of device. Every device will have its own device controller. For example, a disk drive, an audio device, or a graphic. Now, depending upon the controller, more than one device may be attached. One system USB can connect only one. Can connect to USB hub, to which several devices can connect. A device controller maintains some local buffer. Typically, OS have a device driver for each device controller. Now, these device driver understands the device controller and provides the rest of the operating system with uniform interface to the driver. Okay, so what he's saying is, so the job of the disk controller is for memory access. So I have device controllers. Also, each device will have a controller. For example, if you are connecting a USB based device, it will have its a USB controller. If you are connecting external drives, it will have disk controller, and then we will have the CPU. So all of them are connected to the system bus and then the memory. So the role of the device controllers provides access between components and shared memory. Okay, so as I said, every device has a device controller. Typically, OS have a device driver for each device controller. Now, what is a device driver? Oh, let's see this little bit in. Okay. Let's go to now let's see what is a device. A device controller is basically a module that manages and controls the operations. So as I say, every device has its own device controller that is responsible for performing or controlling. So in most cases, we have every devices with their own dedicated controllers. However, we can have a general as well. Then what is a device driver? A device is a software that allows the operating system and applications to interact with the acts as a bridge between the hardware device and software running on the program. Like, why do we need device drivers when we have OS? I mean, okay, now while operating system provides a general platform for managing resources, a device driver is still required to bridge the gap between the OS and the specific hardware devices connected to the system. The OS alone cannot directly communicate with the hardware because it's designed to be hardware agnostic, means it doesn't inherently understand how individual hardware devices are work or how to interact them with them efficiently. Okay, so what he's trying to say is every devices, so the role of the device controller is basically to um, so device controller will control the device. I mean, what's the need to have a USB controller? A device controller is a hardware component that directly interfaces between a specific hardware device controlling its operation. Like, why do we need a device controller? So for example, I have a printer connected to a USB port. Now what's the job of the controller there? The controller will first determine which key is pressed. Is that the controller's job? The OS doesn't need to understand the low level details of how each device works. Okay, so the device control basically is responsible. So when I have a keyboard, let's take a very basic example. So I have a keyboard connected to the USB port. The job of the USB controller is to convert the keystrokes like and check which key is pressed, right? Like that's the then the hardware is responsible for data transfer between the USB and the OS. Okay, so these are external devices, right? The operating system does not know like how or what are these devices being pressed on. Then what's the user device driver? So device. So the USB controller on the mother. Okay, the USB port is the USB controller. What I was trying to say. Okay, so the USB controller is the actual port on the actual USB port on the motherboard is the what he's trying to say is. So USB is the hardware component that manages the USB ports on the motherboard or a separate USB expansion card. The controller is responsible for handling communication between USB. That controls the USB. Why are you saying that controls? Let's see an example of USB controller image. How does it look? Uh, so what is a USB controller? Polling is something else. That is like communication and all. So here he's talking about a USB. No. It's a USB device. Yeah, so this is basically that the physical USB component on the board. It's a specialized IC that facilitates communication between our computer or the host using the universal serial bus. Okay, so this is the so we can say the then what is the why do we have the driver? Why is the USB driver needed? The USB driver is the essence that enables communication between OS and the USB devices connected to the computers. The USB manages the physical connection and data transfer over the USB ports. A software interface to make sure OS and other applications can correctly recognize and interact. So, to sum it up, what we can say is the device controllers are the hardware for each device, and the drivers are basically softwares to understand what that is for. Is it something like that? Yeah, so the actual port is the USB controller or the hardware, and then the driver is basically a software that is a translator between the OS and the okay. So the way that will work is so does okay. So the driver is installed on the OS, right? We need to have the driver installed. So is our drivers below OS like so then what's the job of the OS if the driver is doing if the driver is doing the conversion, why do we need OS? Okay, then the resource management and like which task, how much time should I give it for the CPU, that all perform functions is. So whenever I connect a device, so that specific driver and so the physical device or where it is connected is the USB this is the USB controller, and then I have USB drivers which have been installed on the OS. These are all connected to each other by verbs. Now interrupts. Now consider a typical operation of program performing I/O. To start an I/O operation, the device driver loads the operator registers in the device controller. The device controller in turn examines the contents and determines what action to take, such as read a character from the keyboard. The controller starts the transfer of data from the device to its local buffer. Once the data is complete, then from the device controller, it informs the device driver that it's finished the operation. The device driver then gives the control to the other parts of the operating system, possibly returning the data or printing. For other operations, the device driver returns status information such as write completed or device busy. But how does the controller inform the device driver that data is finished? Okay, now interrupts. Now these are very important thing. What may happen is, now there are two types of interrupts. One is an hardware or other is a software based interrupt. Now what happens is, uh, the USB controller will have all the memory, right? So then from there, with the help of the driver, we need to give it to the OS. So then there may be two types of interrupts. One is hardware interrupt, another is a CPU, a software interrupt. So hardware may trigger an interrupt at any time by sending a signal to the CPU by basically way of system bus. There are many buses, but the system is the main that controls the communication between the components. Now interrupts are used for many other purposes as well as a key part of operating system, how they interact. When the CPU is interrupted, it stops what it's doing immediately, transfers the execution to a fixed location. Then the fixed location usually contains the starting address or the service routine for the interrupt. Or this we will study, like what about what more is an interrupt, what is an ideal time, and okay, what is an IVT or an interrupt vector table, or what is an interrupt handler. Okay, so this is like the more and what happens is when the CPU is suppose, so the device driver basically is going to initiate the IO. This is the IO controller, right? This is reading the data. Then it generates the interrupt. Now this goes to the device driver. The CPU receiving interrupt, then it will go to the interrupt handler, handle the interrupt, process data, return the data. So right now, once we like start, oh, so this is CPU over here. Then is the device driver initiates the IO, like you start the IO. This is the controller. So the IO controller will then, so this keyboard will interrupt the CPU saying no, on hardware this is available. Then it will go handle that data. Then again it will start resuming its own work. Most CPUs have two terms of maskable and unmaskable. This is basically more about interrupts. The thing is interrupts, using interrupts, so there are other ways also, like there's polling that the CPU constantly checks, but the major advantage in interrupt is I interrupt the CPU when I need the CPU time. Whenever my work is over, that the CPU goes back to its original whatever else task it was performing. That way we are not wasting the CPU's time. Remember, CPU's time is of most important whenever we are dealing with the operating system. Okay, storage structure. Now there are two basically. CPU can only load from the memory. By memory, I mean the RAM. The general purpose computers run mostly on their programs for writable memory. Main memory is also called as the random access memory. Main memory commonly implemented in a semiconductor. It is implemented in a form of a semiconductor, that is DRAM. Computers are also other forms of memory as well. For example, the first program to run on a computer power is a bootstrap program, which then loads the operating system. Oh, so okay. RAM loses its content when the power is turned off. We cannot trust it to hold the bootstrap program. Instead, this is for this and some other purposes. Okay, so now CPU will always take instructions from the RAM, but RAM is random access and is volatile. Remember, the bootstrap program needs to be started whenever the computer is turned on. So then, since RAM is volatile, it will get deleted. So then we have for this and some other purposes, the computer, we have something called as electronically erasable programmable read-only memory, EEPROM, and other forms of firmware storage. Okay, now this does okay. The other forms of firmware storage that is significantly written to is another title, EEPROM. We'll study what is bootstrap, why do we need the bootstrap thing. Storage definition, notation. Okay, everything is a bit. Okay, kilobyte is, or gigabyte is GB, that is 1024 bytes. Terabyte or TB. Petabyte is, so it's basically we are considering about powers over here. This is 1024 bytes. So a typical execution cycle executed on a system with a one human architecture. So this now is going to talk about Okay, so now the main memory is too small to store all the programs, but the main memory is from where the CPU will do the CPU. The instruction to be loaded is always should be stored in the RAM. The RAM is something, but then RAM is always limited and it's always volatile. So what we do, we have something called a secondary storage as an extension to memory. The main requirement is that it is able to hold large quantities of data and permanently. So there are two types of devices. One is hard drives and then other is non-volatile memories or HDDs, hard disk drives. So the hard disk drives are basically slower because these are basically from magnetic tapes, and it is slower as compared to solid. Now we have solid state devices, right? HDD. Okay. IO. A large portion of the operating system is basically dedicated to managing IO. Whenever the an operate comes and an interrupt comes, we need to do the movement. Like the OS needs to tell, okay. Now he's saying large portion is basically to manage IO both because its importance on reliability and performance of a system and because of the varying nature of the devices. Recall from the beginning of this section a GPU, a general purpose computer, consists of multiple devices, all of which exchange data via a common bus. Now the form of interrupted is fine for moving small, but this can produce large overhead when used for bulk data. To solve this problem, I have something called as that DIMA. Also, this is again how this is the now computer system architecture. Now this is very important. A single processor systems. So the core is a component that executes instructions and registers for storing data locally. So one core is basically one CPU plus ALU plus other general purpose registers. So when we have a single processor systems, when we have multiple processors, we call it as multiprocessing. Okay, multiprocessor is basically when we have multiple processors. Traditionally, each processor comes with a single CPU, single core CPU, uh, two or more processors, each with a single core CPU. The peripherals, the processors share the common bus and sometimes the clock memory system symmetric. So then let's define what is a multiprocessor system. What is a multi-core system? Multiprocessor is having two processors. Each processor will have their own set of CPUs and registers. So multi-core is when we have different processors on a when we have registers, CPU and ALU on a single chip. Then we call this as a multi-core. Yeah, this is a single processor. We have both two CPUs. Like each of them will have its own registers on a single core. So then we have four cores. That means uh, we have four CPU and ALU, but then they are this is a single core chip, right? By what do you mean by now we have multi-core? Multiple computing cores. Yeah, multiple cores reside on a single. Now these are two different. Okay, so now uh, what happens is if you have CPU and ALU on two different two different CPUs, then first is there would be time latency for what if instruction is one is loaded in CPU 0 and the instruction 2 is loaded in CPU 1. So there would be some time latency, but when they are on the same chip, like when I have four CPUs on the same chip, sorry, when I have two CPUs on the same chip, that is called as multi-core. It is a two-core system. So what will happen is the data transfer or the latency will be less. Nowadays we have many more cores. This is a single processor chip. So like I have two cores, core 1 and core 2. A dual core is basically two cores, but on the same chip, same processor. So what's the difference between a CPU core and a CPU and a processor one? Okay, let's break this down. So multi processor is when we have multiple CPU. Now what is CPU? CPU is the heart. Control processing unit, it basically consists of what does CPU consist of? The CPU has its ALU and a set of registers, control unit and cache. Okay. Now multiprocessor, I will have two CPUs. Two CPUs means each will have its own ALU, CPU, ALU, CU and registers. But when I have a multi-core is basically instead of having two different chips, just make them one. However, they still have different multi-core is basically uh, having two on a single chip. Thereby latency is less. A multi-core is basically a single chip that contains two or more independent processing units called cores. Each core is capable of at its own CPU value. So a quad core has 8. A processor with 4 cores, 204 core is 4, octa is 8. So like I have 8. So cores basically represent CPUs. Yeah, so multi-core processor is basically I have, but then core is all of them are on the same thing, on the same chip. Like there is less latency. So then, but so we can say multi-core is multiprocessing is because I'm having two different CPUs. But a core contains the CPU, right? Indirectly, core basically contains the CPU, right? Each core is essentially a CPU of its own. So when I say, so can we say multiprocessing and multi cores? See, multi-core is basically so this is a multi-core processor. Sorry. You can say I have, see, these are, this is two CPUs, right? And they all have their set of one registers. So then multiprocessor is also same thing, right? So the multiprocessor is have different CPUs, right? But then multi-core is also same. So multi-core is a single CPU or a processor with two or more independent processing units called as cores. They are capable of reading and executing multiple instructions. Execute a single. Okay. So is he saying? So what he's saying is like these individual chips are the processors, right? But there it's on a single chip, so it's called as a single processor, but multi-core. They I have different processor. Oh yeah, it's something like this. So multiprocessor is two different CPUs. CPU chips. And then multi-core is also like multi only difference is the multi-core, it will be on a single chip. Yeah, the major difference between multiprocessing and multi-core is multi-core is a single chip, but then I have different processing units on it. So means multiple cores on a single chip. As 4 cores on a single chip, but yeah, multiprocessing means different physical CPUs. Seeing I have multiple physical CPUs. What is the example I was given? A server with 2 processors, each with 4 cores. So I have 2 different processors, and so I have 2 different chips. On each chip, I have 4 cores. So you have 2 separate chips, and each chip has multiple cores. But then multi-cores basically contains the CPU, right? Only thing is it is on a single chip. No, that's what he has mentioned. See, he has separated this is processor 1, this is processor 2, but these are on 2 different chips. But then in multi-core, what he will do is this is a single processor, and then although each CPU will have its own registers and cache, but then they will be on a single chip. CPU, the hardware that executes the instruction. A processor is a physical chip that contains one or more CPUs. Core is basically the basic computation unit of CPU. Multi-core is multiple computing cores on the same CPU. Multiprocessor is basically that has multiple processors. But although virtually all systems are multi-core, we use general term CPU when referring to a single computational unit of a computer systems, as well as multi-core when specifically referring to one or more cores of a CPU. Now, blade servers are with okay. So now cluster systems is basically which gather together multiple CPUs. Yeah, so we can create a cluster, right? Okay, so now this is how this is a motherboard, how it looks like. Okay, so this is where our CPU is going to come in. This is a fully functional computer. Then I have different slots. This is for the bus. This is for my USB drives. This is for my DRAM or the what CPU will access. Okay. Now computers, and I have a single. This is the structure of a cluster system. A cluster system is the one because we have a single. When we say create a Hadoop cluster, so what is going to happen there? So what is now he's talking about cluster systems. How do they look like? For example, generate a cluster when we say. Oh, so clustering is also of 2 types: symmetric and unsymmetric. Clustering can be of asymmetric and asymmetric. In asymmetric, machine is on not standby mode while the other is running application. The all standby machine does nothing but monitor the active server. If the server fails, the all standby becomes the active. So then I say create a Hadoop cluster. What? Okay. Clustering means. So what do we mean by an Hadoop cluster? It is basically CPUs, computers that work together to run Apache Hadoop. Okay, let's see what happens here. Yeah, it's the same thing. So is the file system and map reduce. Okay. I think multi-core. Multi. Multi-core is, so this is architecture. How each of them. This is a both a multi-core and a multi-processor, but then this is both, right? I have two processors. It should be on a single chip. They shouldn't have. What is a multi-core processor? But then doesn't these two become two different types of uh, so multi-cores is the one that is responsible. So the more number of cores, more faster is the processing, because then it will be on a. Is there a multi-processor? I have multi-processor computer. Which is that? So let's say buy multiprocessor. Oh, see the price. Also, these have so many CPUs, like racking of CPUs. Some when we have these are all CPUs, I guess. 1, 2, 3, 4. This is this is 24 cores. Damn, 24 cores. Just imagine the number of cores. 24 CPU cores. But then how do we change between CPUs? Like how does the multiprocessing happen? Cores is basically on the same chip, right? But how do we switch between? So when we use multiple CPU, the OS does. The context switching should happen between the OS as well, or CPU as well as, and then there should be scheduling as well. Also, my is Mac Mini. Let's say Mac Mini. Mac Mini 2024. But specs, let me see. Okay, it has 8 core, 4 high performance cores, 4 high efficiency cores, 8 core CPU, 10 core GPU. GPU is so okay, CPU and GPU. So it has a different Just a different processing unit for GPU. So 8 core means 8 ALU CPU and registers on same chip. That's what he's trying to say. So the more ALU that means, just let's see. When I say we say 8 core, it means the processor chip has 8 separate CPU processing on. How does that mean that 8 separate ALUs and registers for every core? Instead, each core is complete unit that contains one set of registers and ALU and other components required to. Every core has its own. Yeah, so every core has its own thing, right? Has its own ALU, registers, and control unit. Yes, exactly. Multi-core means so every will have in its own, but then all of them will be on a single chip. All on a single chip. So I have 8 cores, each having its own ALU CPU combination. Then that is what so like I mean it might be, let's see, M2 chip architecture. Does it the Apple M2 do we have? Oh, so I have the this is okay. So now let's visit this Mac. What is this? So is this, why is Sephora coming up? Where is the ALU and CPU of M2? I need to check. Yeah, it's on this single chip, right? This is the one. Apple's ALU architecture. So where are the 8 cores? There should be somewhere. This is the CPU, this is the GPU, both are separate. The CPU has, now why is the 8 cores? M2 chip 8 cores. Oh, this is more. This is a 10 core one, but let's, where is the diagram? Oh, yeah, it is. This is 10 core. I have 10 cores over here. Where is the core on the chip? No. What I mean, chip image. It might be somewhere on the chip. Not able to get an. I don't know whether they have. There should be a documentation somewhere to have the scores. We will see that later on. Let's not go ahead. Okay. Then the operating system operations. Now that we have discussed about computer system organization and architecture, we are ready to talk about operating systems. An OS is an that provides the environment within each programs are executed internally. For a computer to start running, for an instance, when it is powered up or rebooted, it needs to have an initial program to run. As noted earlier, its initial program or bootstrap program tends to be simple. Typically, it's stored within the computer hardware in firmware. It initializes all aspects of the system from CPUs to device controllers to memory contents. The bootstrap program must know how to load the operating system and how. Yeah, so I said that clustering thing, right? This is basically how to big data cluster. Okay, once the kernel. Okay, now see what he's saying is. So the bootstrap program is basically, or the boot. Now we have discussed using an operating system provides environment. We have to it runs an initial program to run. As noted earlier, this initial program or bootstrap program tends to be simple. It is stored within the computer hardware in firmware. Now what is this firmware part? So I said computer hardware in firmware. Where is BIOS stored? Like where does that come from? But what is a firmware? Firmware. I say a firmware. This is very commonly used term. A firmware is a software that is embedded directly into the hardware devices to control. It is stored in all volatile. Your device would function. A firmware is low level. Where does the BIOS come from? The BIOS of the Unified Extensible Firmware is that initializes the computer hardware components during boot up before handing control over to the operating system. Now, who develops the firmware? Firmware developer. What do I mean by firmware? Okay, so for example, if I'm using MSI, MSI mother. Oh, so the company that develops the motherboards also has the firmware developed. That goal is basically to initialize everything, but the motherboard manufacturing produces the firmware, but components can be any. How does the firmware know about the components? You can have any, right? When you do an assembling, you can. Firmware. Okay, when you power on your computer, the firmware is the first software to run. It has a crucial job to initialize. Then how does the firmware? Oh, so the SATA, BATA, the chipset. Each component of motherboard typically has configuration data stored in EEPROM or a separate ROM. So the firmware uses data to know how to communicate with the devices. The CPU. Oh, RAM. Then again we have DDR4. So basically, firmware developer is the one who is going to. How does it know about specific devices? Okay, so communication. When I say a firmware update, oh, so when So there is a difference between a firmware and a software update. So firmware update is basically related to the all possible chips that can connect, like initializing all possible chips. It's a program, so hence it is a software. Is that so? So when I say a firmware developer, so where is this firmware stored, like on the motherboard? So I can say, what does firmware mean though? Firmware meaning in English. The term firmware refers to a software that is permanently programmed onto an hardware. It is permanently programmed. Okay. But the motherboard comes in with a motherboard has a ROM. By the motherboard come basically, but it's the motherboard has a RAM or a memory that comes in. MSI ROM image. It should not generate a new one. Let's say MSI firmware MSI firmware, where is it stored? Oh, this is the okay. MSI. Cannot get nflash to see any BIOS file. So MSI machines support a single method for updating, so that is through the .exe file released by MSI. Since MSI supports Windows, these are all except. Is there any images? Images is not good, right? Where is the unbuilt RAM? Like, where is the BIOS? There should be some. Let's see, MSI. Motherboard. There should be a RAM on it or something. Oh, it's a chip. Where is the BIOS? Oh, this is the BIOS. It is usually located at the bottom of the board next to PCI Express slots. Yeah, so this is where it is present. What is this? Win bound something. This is done by the its purpose. It can be anywhere on the BIOS. Let's say this. Okay, so firmware is basically the motherboard software that is going to initialize all other devices and load the BIOS. Once the BIOS is available, then it will invoke. Then it will invoke the operating system. Then is when. Okay, now see now okay, now what we want to check is what is a multiprocessing. So multiprocessing, as we considered, we have what is a multiprogramming and multitasking. Okay, when we can run more than one program at a time, it is called multiprogramming. As well as keeping users satisfied by organizing, so that in a multi-program system, a program execution is termed as a process. Okay, I have multiple programs that can be run. Now multitasking is a logical extension. What happens in multi-programming is like CPU can only execute one program, right? So what happens is it kind of does switching between the programs, but then this is done by the OS. The OS may make sure that the switching is done in such a way that the CPU is busy always. Yeah, so I have different processing, like process 1, 2, 3, 4, and then using CPU scheduling will so dual mode and multi-mode operation. Generally, since we say OS acts as like an interface, so then there is something, some functions are reserved for only for the OS, whereas some the user can interact. Timer is basically to make sure everything is completed within a specific amount of time. Memory management, again, this is all done by the OS, like file management, OS management, and everything else. So like this is how from a magnetic disk does it come into CPU. Virtualization, what is a virtual machine? Yeah, this is another important. Okay, now what's a virtual machine? Let's see, let's check an overall of all. Okay, so where we studied about memory management is basically we have the von Neumann architecture, very famous. Remember, we have the physical, the main memory called as the hard drive, and then the secondary is the SDD, or the main is the RAM, second is the ROM. RAM is volatile. The moment we switch it off, it will go out. CPU will always access the RAM. Then this file system is storing files into different, organizing our storage, like how can we have different files, then and the operations performed with them. Caching is another important part. It's used, right? We use for example, what does it does is it kind of information is normally kept in some storage such as main memory. It is copied into a faster storage system, the cache, on temporary process. When we need a piece of information, we check whether it's in the cache. If it's in the cache, take it from the cache. It kinds of helps in increasing the speed. Like certain information can be stored on cache, but remember, caches are always smaller in size. Like you won't get a cache of like 1 TB. It's very small. So the information told on the cache should be very, very, very important. We have cache measurement. They are limited sizes and very small in sizes. So this is basically how from magnetic disk it's getting to an hardware. Then the I/O is basically when we have different components considered, how to manage them. Always remember, we don't want the user directly to access the hardware. We need proper authorization. CPU does this. See, the OS is responsible for this protection and security. Okay, now virtualization is a technology that allows us to abstract the hardware of a single computer, thereby that each separate environment is running its own private computer. These environments can be viewed as different individual operating systems and maybe running at the same time and interact with each other. A user of a virtual machine can switch among various operating systems in same way a user can switch among the various processes running concurrently in a single virtualization. Now, what is virtualization? What we do? What happens when we do a virtual machine? A computer is running a single operating system. Okay, so what is then this? I can have multiple operating systems, but then I need to have something called as a virtual machine manager allocated that will help me to switch. So many people have two operating systems involved. One is okay. Virtual machines. Virtual machines is basically having more than one OS. Is this what we say? Oh, why is it a virtual machine? Oh, because the actual hardware is only one. Okay, that runs another inside another. It's a physical computer. So virtual means something that is fake, right? Virtual meaning is it's more virtual means something which is not real, not in physical form. Okay, so we create a simulation that, so like when we have two OS, a virtual machine not necessarily having two operating systems on the same machine doesn't count. Or dual boot, we can have two operating system installed. We can choose boot manager. A virtual machine is a software based emulation of a physical it's basically a program. It's not an actual thing. When I say Linux virtual machine, what I'm going to do is, so install Linux virtual machine on your computer. It's a software. And then I have different computers, right? Start 1, start 2, start 3. And then I will have something called as a machine manager. It will help me to switch. However, it will be on a single computer. So dual booting is we are having more than one OS at a time. Multiple OSs running simultaneously. So they will. Oh yeah, when we say like either we can. So nowadays we have dual boots, right? Either we can use iOS OS or some other Windows OS at the same time. The multiple virtual machine is basically these are running simultaneously. It's what is a virtual? I have a virtual box, right? Yeah, create a virtual box. Virtual box is a virtual machine. Yes, a hypervisor that allows you to run multiple operating systems simultaneously on same physical computer. It is type 2 hypervisor. It means it runs on the top of an existing OS rather than directly on your hardware. What is an hypervisor? Hypervisor is the same, right? That creates and manages a virtual machine allowing multiple OS to run simultaneously on a single physical computer. It is a critical component. Okay, so now there are two types of hypervisors. The hypervisor is a software that creates and manages virtual machines. So the management of these virtual machines is done by something called an hypervisor, which allows multiple operators to run we are running it simultaneously. This is what is important. We are not running one at a time. Both of them are running. On a physical computer, its critical component is virtualization, enabling the effective use of hardware resources by dividing them into two separate, isolated environments. So what does it do? It runs off on top of an OS, and then the virtual machine runs on the top of the OS. It uses the resource provided by the OS and generally easier to set up and use. It is less efficient than hypervisors. It's a type 2 hypervisor. Hypervisors are basically, okay, as I see, the physical hardware is of the computer, right? The virtual machine created by a hypervisor, it uses the physical hardware of the computer, but they through a virtualized environment provided by the hypervisor. Did something happen over here? Is it still recording? Oh, it's on streaming, but it isn't. Okay. So, yeah, so let's complete this. So basically, a virtual machine uses the physical hardware of virtualized hardware. What do we mean by virtualized hardware? What is it trying to say? Virtualized. What do you mean by when you say virtualized hardware? Okay, a virtualized hardware is this is not a physical one. However, it is not the physical hardware is of the whatever computer spec you have, right? The virtual portion of the physical CPU goes to a Linux VM. The Linux OS thinks that it has two virtual CPUs, 4 GB of virtual RAM, 50 GB of virtual. It does not know if it's sharing these resources with the Windows OS. Oh no, wait, let's see what happens is. What is by virtualized hardware? What does he mean here? Abstracting the physical hardware of a computer and presenting it in a virtual version. Although the hardware is one every is it something like is one the virtualized hardware one thing we have separate physical hardware even though not present. Is that why it is? Yeah, so each page that it has an own dedicated physical, so whenever you do you configure, right? 10 GB RAM, 12 GB RAM. Yeah. However, it says the same physical adder powered by the host. Host is basically the partition which the so whenever you install a Linux VMware, right? So the moment then you need to install an OS as well. So that OS will think, yeah, I'm the only person who is using this, but in fact, the You can have multiple OSs also, right? So they will each OS or each instance is like a small computer which has an OS, but but it's not physically, it's like a software thing. Oh, this distributed systems is basically we have DCP, kernel data structure. Okay, we can. How is the kernel made? So this is not that important here. Client server architecture, right? This is the most common thing we have. So voice over, yeah, this is something peering. Then we have different types of cloud connections. Oh, real time. This is most important thing, RTOS. Because that monitoring happens in real time, so it's called as real time. In plane, right? We need to inform the pilot about the weather condition. It's having in real time. That's all for this lecture. See you guys in the next one. Thanks. Bye.